So now we want to start looking at a whole bunch of different tests to determine if an infinite series converges or diverges. And in some cases, we'll also be able to tell what the series converges to. But for the most part, we're mostly just going to be focused on if it converges at all. For a lot of different theorems and stuff where we use these kind of techniques in these series, we really only need to verify that they do converge, not necessarily what number they converge to. So let's go ahead and look at our first one is actually called the divergence test. So kind of the opposite of this. Okay, so this one is not actually testing for convergence. This one is testing whether or not something diverges, which is also helpful because if it diverges, that tells us it doesn't converge. So let's consider the limit. Well, first of all, let's just say we have a sequence a sub n, right? And we want to consider the series n equals 1 to infinity of this sequence. Okay, so the sum of this sequence. So using a little bit of algebraic manipulation here, we know that the limit as k goes to infinity of a sub k, where k is one of these terms, this is equal to the limit as k goes to infinity of s sub k minus s sub k minus 1. Okay, so if we just think about why that's true, remember this is the kth partial sum. S sub k would be 1, or sorry, a sub 1, I should say, plus a sub 2, all the way up to a sub k. S sub k minus 1 would be the same thing, but up to k minus 1 instead. Okay, so if we subtract these two, what we're going to be left with, see, these terms will cancel, etc. The only thing that'll be left is this a sub k term. Okay, so we can see that this first equality is true. Now, if let's write this down first. If n equals 1 to infinity of a sub n is less than infinity, meaning that it converges. Okay, so if this sum of this sequence converges, then we can get this next equality. We'll actually first we'll use the limit property to break this up. Okay, so this is the limit as k goes to infinity of s sub k minus the limit as k goes to infinity of s sub k minus 1. And now we can use this next equality to get that this is equal to s minus s. Okay, so the limit as k goes to infinity of s sub k being equal to s, that's given to us from the fact that it's a convergent series, right? If their series is convergent, then that means that the partial sums, the sequence of partial sums converges to some real number s. That's basically the definition of convergence, right? S sub k minus 1, just because we move the index down 1 isn't going to change what that sequence is converging to, right? We've kind of seen that in different forms that we can kind of play around with the index. I know we looked at the limit as n goes to infinity of like a sub n plus 1, and we saw it should be the same thing as the limit as n goes to infinity of a sub n kind of thing, right? So when we're going out to infinity, that one extra term that we're losing there isn't going to make a difference in terms of the limit, at least. So these are both going to be equal to s. And of course, the difference here is 0. So what we're getting from this is that if the infinite sum of this sequence of a sub n is less than infinity, then the limit, and we can just write n to infinity this time, we don't have to use the k, that was just to show the partial sums, then the limit as n goes to infinity of a sub n is equal to 0. Okay, so this is something again, I think that I talked about this in an earlier video, so now we're just kind of like making it more rigorous, more we're like writing it down as a definition here. In order for the sum to converge, the limit of the sequence must be 0. If you think about why that's true, I think it should become pretty clear. If you think about, like, say that the limit of the sum or the limit of the sequence is 1, for example, then that means that you get to a point eventually where you're just infinitely adding ones, meaning the series cannot converge, right? It's just going to keep getting larger and larger indefinitely. In order for the series to have any chance of converging, that limit has to be 0, because you want to get to a point where eventually the series is not increasing at all, right? As you go out to infinity, you're basically adding 0 each term. So that series is not increasing, so now it has a chance to actually converge to a number. So the to flip this around, what we would say, which is the test for divergence. Okay, the test for divergence says that if a sub n does not go to 0, okay, this is one way to write does not go. You do an arrow and you do a line through the arrow. As n goes to infinity, then that sum of that sequence diverges. Okay, so it diverges. So this is basically the what we would call the contrapositive of this first statement, right? So we flip it around and negate it. So if a sub n, if that limit is not 0, then we know right off the bat that the sum diverges. So this doesn't help us to determine if the series does converge. Okay, so just because we know that the limit of the sequence is equal to 0, that doesn't automatically give us that the series converges. But what it does give us is a nice, easy way to eliminate convergence right off the bat. We can just take the limit of the sequence, and if it doesn't equal 0, then we know right away that there's no hope that the series converges, and then we don't need to do any other test. So this is basically the first test you would ever want to do to test for convergence, because if the limit is not 0, then you're done. But if the limit is 0, you're going to need to use another test, because that alone doesn't tell us that it converges. Okay. So what we would say here is that the converse is not true. Okay. So the converse here would be when you flip the statement around, meaning that if if the limit is 0, then this converges, and that's not necessarily true. Okay, so a good example of that is this sequence of 1 over n. Okay, so we've already said a couple of times that this does diverge. We haven't actually shown it yet, but this is like kind of like the canonical example of this kind of idea, that of course the limit as n goes to infinity of 1 over n is 0, but this still diverges. Okay. And by the way, this does have a special name. This is called the harmonic series. Okay. And we will show that this diverges eventually with one of our tests. So just looking at a few other examples here for this test of divergence. So if we're presented with the sum of n equals infinity, or n equals 1 to infinity of n over 3n minus 1, first thing we want to do then is test the limit as n goes to infinity of n over 3n minus 1. Okay. And when you do this, you should get 1/3. Okay. So the pattern for these kind of sequences is that it's just the ratio of the leading coefficients, but you can show this by force factoring, or even L'Hopital's rule. would work out fine. So we know right away that this diverges. Okay, so we don't need to do any more work here. Another example, n equals 1 to infinity of 1 over n cubed. Okay, so when we take the limit here, this does equal 0. Okay, so this tells us that we can't rule out that it converges. It might converge or it might diverge. So it's kind of like it's inconclusive. Okay, so I guess if we're just looking at an answer for the test for divergence, we would say is inconclusive. Last one here, n equals 1 to infinity of e to the 1 over n squared. Okay, so here we have the limit as n goes to infinity of e over 1, e to the 1 over n squared. So remember, you can take the limit into the exponent here. So this is equal to e to the limit as n goes to infinity of 1 over n squared. This part is 0. So we get e to the 0, which is equal to 1. So it's not equal to 0. So again, this tells us right away that it does diverge.